Hello students, this is our tutorial of today we will discuss about groups and how groups are formed and what its properties. How groups are formed and what its properties. So let's start. Uh, Before to know about groups, we need to know about binary composition. What is a binary composition? Here we write binary composition. Binary composition basic to know to formulate any group. It is important to know and how it works. Binary composition. Binary composition is such kind of operation. It is called a operation, mathematical operation on any set. Take a set S. Its have elements. Take such that 1, 3, 5, 7, 4 elements and 2. So this group S has 4 elements 1, 3, 5, 7. Now any operation, binary operation, is such kind of such that on the set S it can be written. Take a binary operation, you can give omicron. Omicron is a very small o. This is called omicron. Omicron is just showing the binary composition together with the set S and with the binary operation omicron. We have some properties which the elements of the set is must obey. So first, that any element of S with this operation, if it is closed in this with this set with this binary composition, then it is with omicron any binary operation, then it is a binary composition. Means that take like I'm just giving example. Like take omicron or binary operation is our addition. Addition is a binary operation. Now here any element to any two element 1 plus 3 is equal to 4. So 4 here does not exist. So this binary operation here does not form say binary composition. But if we take in place of this, if we take the set of natural numbers, is equal to natural numbers, then 4 must exist in n. 1 and 3 exist and 4 also exist. If you do any two elements, get any two elements, 2 plus 7, all exist in the natural numbers. So here 9, it also exists in n. So here n with the binary operation addition forms a binary composition. Important. You can take the binary operation subtraction also, multiplication also, division also, but mostly used plus and multiplication. Addition and multiplication are mostly used in binary composition. So it is about binary computation. Now, to formulate a group, form a group, we need to know some properties. Take a property like closure property. What is a closure property? Closure property. Closure property means uh, any set with its binary operation. I already said I am now giving star mark in place of omicron. This is a binary operation. So any two elements in this set with this binary operation like A star B must exist in the set A star B must exist in the set S. If this property happens in the with the set S, then we will say that S is closed with this binary operation. What will we will take the binary operation? So we have taken an example n and a set of natural numbers and addition is a binary computation. So we will find that it forms it is closed with this binary operation addition. Like any two elements if you add, then you must get in this in the set natural numbers. So take C belongs to n and D belongs to n, then always you get C plus D, the binary operation plus addition C addition D must exist in S. So here closure property is satisfied. So here n and set of natural numbers and addition satisfies the closure property. If another binary operation and another set satisfies this also, it must satisfy this closure property. Now we have to know about associativity. What is associativity? Associativity axioms is that associativity axioms is that here any set is and binary operation we are taking star. If any three elements we will take any three element A actually this is actually E, B and C, any three elements in S. If they satisfy this property A star binary operation B, the first bracket means this operation will happen first and then the second operation will happen with C. This operation is it means that this operation will be first, then the real will operate with C. With this binary operation is equal to A binary operation B binary operations. If we take second and third elements operation first, and then then do the remaining with the first element, it must satisfy the operation of the first two elements with the third element. Here, A, B, C, the order A is in first first element, it is second element. The order must not be changed. You cannot put A at the last. Here, A must be the first element, B must be the second element, and C must be the third element. So, what are you if you will not change? And this, if this happens, then we will say that S is associative with respect to this binary operation. Now, I have given an example: natural numbers, set of natural numbers, and a binary operation addition. This is also associative. You can very easily verify that any numbers 3 plus 2 plus 5, what will we get is equal to must equal to 3 plus 2 plus 5. So here with this binary operator addition, the set of natural numbers are associative. This is the property of associativity. Now, what is identity element? Identity element. What is identity element? Identity element. A set may have many elements, but which element is we call the identity element? If a set is the binary composition star, if satisfies a condition that any element with another element, say that giving the element E, both are belonging to S. Now, if it happens that A binary operation with the element E equals to A, then we say it is right identity element. Right identity element. E is called right identity element. Right identity element. And if you will take E with the binary composition A, we will get A. Then E here E here E is a right identity element. Here in the second case E is a left identity element. And if both cases happen together, then we say A equal to E identity element E. If both the cases happen at the same time, then we can simply say that E is the identity element. Otherwise, if it is not clearly written, then you have to take that right element or right identity element or left identity element. It always you cannot get always that right and left element are equal. You can happen in such cases that right identity element and left identity element may differ. So you need to know this condition that the two cases must be satisfied. Then we can call that E is the identity element of the set S. Now, natural numbers, I have given natural numbers have no identity element. with the binary composition addition, it does not have any identity element. So how we can take an example? You take the set of integers. Set of integers have identity element with respect to the uh, binary operation addition, because uh, set of integers consists of 0. 0 is such a element that works like a identity in the set of integers. Any element, if you take in set of integers like a belongs to I, then you must get this condition fulfilled. A plus 0, a plus 0 equal to a equal to 0 plus a. That's why we get in this example, set of integers with the binary combination addition, we must get an identity element. But though it satisfies closure property as property, it does not have any identity element. Set of natural numbers with the binary operation addition. Now we will take another example, another condition. What is uh, inverse element? Inverse element. Inverse element in a set, we have to find out. Inverse element such like it is defined. Take set is and binary operation. If you get any two elements A and B in the set S, then if it is satisfied that A, and we know that E is the identity element, it is the identity element in it. We first assume we have already cautious or already known about that E is the identity element in S. Then if A star B is equal to identity, then we say that B is the left inverse. This is the B is the left inverse of A. B is the left inverse of A. Inverse of A. And if B is the binary operation A is the identity element, then we say that A is the B is the right inverse inverse of A. So if both the cases happen together, then we simply say that B is the inverse of A. Both cases if happen together, then we say B is the inverse element of A in the set is inverse element of A. So now we will take an example of we have already seen that set of natural numbers with the binary option addition does not have any identity element. So set of natural numbers does not have any inverse element also. So set of integers with the binary composition addition, it have a identity element 0. It have a identity element 0. So it may have inverse elements. So we will try to find out. Now take the any element 2 in the set of integers. So we'll get minus 2 as the inverse element of 2, because 2 plus binary operation is plus minus 2 minus 2 also belongs to the set of integers is equal to 0, the identity element in the set of integers, and minus 2 plus 2 also is equal to 0. So this satisfies the set of integers with the binary operator addition. Have every element uh, must have an inverse element. It is compulsory that not for any element, but for every each element in this set, there must have an inverse element. Then the inverse property is satisfied. If the fourth set property I have already discussed, closure property, associativity, uh, identity element existence, inverse element existence, four property satisfied in any set, then we say that then the set will form a group. Then the set form a group. So necessary condition for formation of a group, formation of any set, group formation of any set, set is with respect to the binary operation that happens when first property, closure property satisfied, second property, associativity satisfied, third property, I said existence of identity element. Identity element must exist. We must find out an identity element in S element must exist, and what I have said for the exam that for each element there must have an inverse element. For each element there must have an inverse element. Then we say that the set forms a group with this binary operation. Not for all binary operations, just for like integer with respect to the binary operation addition satisfies all these properties. It have closure property, you can verify associativity, it have identity element G2 and inverse elements for each element in the set of integers. So it forms a group. But set of natural numbers does not form a group because it does not have any identity element and not inverse elements for each element. If it does not have identity element, then never have any set inverse elements. And set of natural numbers with respect to the binary operation addition does not form any group. It does not form any group. So you can understand now how a group can be formed. Now I am giving a simple example. Hmm. Both sets are infinite. Identity a set of integers is a infinite set. Now I give you a finite set which forms a group. Very important. You have to understand that it is a finite group. Means its coordinate is finite. Take a set S of three elements. We know the square, the cubic roots of 1 are what? 3 cubic roots are 1 omega and omega square. Now we know the relation also that omega cube must be equal to 1 and 1 plus omega square is equal to 0. These two uh, property. We already familiar with this. It is from part of the um, roots of a algebra. So you know about this. So we will take the three elements uh, in the set S, 1, omega and omega square. Here we will take binary operation different. Here the binary operation will be multiplication. We will take multiplication as the binary operation, multiplication. So how can it prove? How can we prove that it forms a group or it does not form a group? I'm giving a table to clear it. Take a table for three elements. Now look at the binary operation I am taking multiplication. Multiplication is the binary operation. Now 1 omega square. But here from omega and omega square. I am taking to verify if satisfies the closure property or not. Closure property you already know that for with this binary operation multiplication of uh, any two elements uh, of of the set, the binary the resultant element must be in the set S. So here it will be 1 multiply 1 is 1, it belonging to S. 1 multiply omega is omega. 1 multiply omega square is omega square. So the first row you are looking at all the elements belonging to the uh, one to the set S. So with the multiplication of 1, all the elements giving the same elements of the set S. Now with the multiplication of with omega, the three elements giving omega, here omega square, and here we get omega cube. Omega cube we already know that it must be 1. So here will be 1. Then we are getting the three elements again. And now here we will get omega square, omega cube into 1. Omega 4 means omega cube into 1. Omega 4 is equal to omega cube into omega. It will be 1. That's what we will get omega. So you are looking that any two any multiplication between any two elements of the set giving the and giving such element that belongs to the set is, so it is closed. One property is satisfied. Now you can very easily verify the other property. Associativity 1 omega, and I am giving dot. Dot is just implying this is equivalent to dot. Dot is just implying that multiplication. Dot omega square. So it must be omega and omega square. And if we multiply further, then we will get omega cube, and at last we will get 1. Now if we will do in this in the another way, 1 omega square, then we get 1 Then 1 omega cube will get 1. So both are equal. Then this is these three elements also associative. The set is associative. Now to find out identity element, can you guess what is the identity element of the set? Of course 1, because 1 is the same element. If we take the identity element 1, identity element 1, 1, then omega with the multiplication operation we get omega, and the left inverse and the right inverse also. So 1 is the inverse of omega, and also the other element also should satisfy. 1 multiplication of omega square, we get omega square multiplied equal to omega square multiplication 1. So both elements are satisfied with the identity element 1, and we are getting the same elements. Also 1 is with itself is identity. 1 multiply 1 is 1. So 1 is also the identity of itself. So there is also identity element. And now we will take the inverse elements. To find out the inverse elements, we have already found out the identity element, which is 1. Now we find out the inverse element. 1's inverse element is 1, because 1 multiply 1 is 1. So 1's inverse element is 1. Now omega's inverse element, what will be? Omega multiply 1, omega multiply omega square is equal to omega cube, that is 1, and omega square by omega. So here you can very easily note that omega is the left inverse of omega square, and right inverse also of omega square. So omega's inverse element is omega square, and omega square's inverse element is omega. Both are just mutually dependent, because uh, one's inverse element is another, and another's inverse element is the earlier one. So here we are getting the inverse elements of the three elements. So yes, satisfying with this binary composition multiplication all the four axioms. So yes, must form a group. So it forms a group. It forms a group. Now last one I must want to discuss. What is abelian group? What is abelian group? Now group we have already known. What is a group. So in which condition we will say that abelian? Abelian group, if one more axiom is satisfied, we will say this is a abelian group. For being a group for a set with a binary composition, we need 4 axioms. If we add one more axiom with the condition that any two elements A and B of the set A, if we find, here we get the giving star any binary operation. Here any binary operation, we will get B binary composition A, then we will say that the group is abelian. Here, yes is abelian or not, this is a homework for all of you. You have to comment me that yes is abelian or not. I must check this from all of you. You will have to comment me. This is your homework. Must send me in my comment box. And thank you. Subscribe this channel. Subscribe. I'm continuing launching videos just for all of you. And if you subscribe, you will get first to view first. You must need to subscribe this channel. So subscribe this channel and share with your friends. This is a request you can say that share with your friends to make them know about this video and enjoy mathematics topics in this channel. Thank you very much.